As an introduction to the uncertainty principle, we're going to talk about waves and how waves are related to each other. We'll get into a little bit of the context of Fourier analysis, which is something we'll come back to later. But the overall context of this lecture is the uncertainty principle. And the uncertainty principle is one of the key results from quantum mechanics, and it's related to what we discussed earlier in the context of the boundary between classical physics and quantum physics. Quantum mechanics has these inherent uncertainties that are built into the equations, built into the state, built into the nature of reality that we really can't surmount. And the uncertainty principle is one way in which those, or is the mathematical description. It's those relationships that I gave you earlier. Delta P, delta X is greater than about equal to h bar over 2. I think I just said greater than about equal to h bar earlier. We'll do things a little more mathematically here, and it turns out there's a factor of 2 there. To start off, though, conceptually think about position and wavelength. And this really is now in the context of a wave. So say I had a coordinate system here, something like this. And if I had some wave with a very specific wavelength, you can just think about it as a sinusoid. If I asked you to measure the wavelength of this wave, you could take a ruler and you could plop it down there and say, okay, well, how many inches are there from peak to peak? Or from zero crossing to zero crossing? Or if you really wanted to, you could get a tape measure and measure many wavelengths, 1, 2, 3, 4 wavelengths in this case. That would allow you to very accurately determine what the wavelength was. If, on the other hand, the wave looked more like this, give you another coordinate system here, the wave looked something like this, you wouldn't be able to measure the wavelength very accurately. You could, as usual, put your ruler down on top of the wave, for instance, and count up the number of inches or centimeters from one side to the other, but that's just one wavelength. It's not nearly as accurate as, say, measuring 4 wavelengths, or 10 wavelengths, or 100 wavelengths. You can think of some limiting cases. Suppose you had a wave with many oscillations. It looks like I'm crossing out the wave underneath there, so I'm going to erase this in a moment. But if you had a wave with many wavelengths, and you could measure the total length of many wavelengths, you would have a very precise measurement of the wavelength of the wave. The opposite is the case here. You only have one wavelength. You can't really measure the wavelength very accurately. What you can do, however, is measure the position very accurately. Here, I can say pretty certainly the wave is there, plus or minus a very short spread in position. The other hand, here, I cannot measure the position of this wave accurately at all. If this thing continues, I can't really say where the wave is. It's not really a sensical question to ask, where is this wave? This wave is everywhere. These are the sorts of built-in uncertainties that you get out of quantum mechanics. Where is the wave? The wave is everywhere. It's a wave. It doesn't have a local position. It turns out, if you get into the mathematics of Fourier analysis, that there is a relationship between the spread of wavelengths and the spread of positions. If you have a series of waves of all different wavelengths and they're added up, the spread in the wavelength is related to the spread in positions of the sum. And we'll talk more about Fourier analysis later, but for now, just realize that this product is always going to be greater than or equal to about 1. Wavelength is something with units of inverse length, and the position, of course, is something with units of length. So the dimensions of this equation are sort of a guideline. Wavelength and position have this sort of relationship, and this comes from Fourier analysis. So how do these waves come into quantum mechanics? Well, waves in quantum mechanics really first got their start with Louis de Broglie. I always thought his name was pronounced de Broglie, but it's, well, he's French, so there's all sorts of weird pronunciations in French. De Broglie is my best guess at how it would probably be pronounced. De Broglie proposed that matter could travel in waves as well. And he did this with an interesting argument on the basis of 3 fundamental equations that had just recently been discovered when he was doing his analysis. This was in his PhD thesis, by the way. E equals mc squared. You all know that equation. You all hopefully also know this equation, E equals hf. Planck's constant times the frequency of a beam of light is the energy associated with a quanta of light. This was another one of Einstein's contributions, and it has to do with his explanation of the photoelectric effect. The final equation that de Broglie was working with was C equals f lambda. The speed of light is equal to the frequency of the light times the wavelength of the light. And this is really not true just for light. This is true for any wave phenomenon. The speed, the frequency, and the wavelength are related. Now, if these expressions are both equal to waves, or are both equal to energy, then I ought to be able to say mc squared equals hf. And this expression tells me something about f. It tells me that f equals c over lambda. So I can substitute this expression in here and get mc squared equals hc over lambda. Now I can cancel out one of the c's, and I'm left with mc equals h over lambda. Now what de Broglie said was this is like momentum. So I'm going to write this equation as p equals h over lambda. And then I'm going to wave my hands extraordinarily vigorously and say, while this equation is only true for light, and this equation is only true for waves, this is also true for matter. How actually this happened in the context of quantum mechanics, in the early historical development of quantum mechanics, is de Broglie noticed that the spectrum of the hydrogen atom, these bright line spectra that we were talking about, where a hydrogen atom emits light of only very specific wavelengths. Intensity as a function of wavelength looks something like this. That could be explained if he assumed that the electrons were traveling around the nucleus of the hydrogen atom as waves, and that only an integer number of waves would fit. The one that I just drew here didn't end up back where it started, so that wouldn't work. If you had a wavelength that looked something like this, going around, say, 3 full times in a circle, that would potentially account for these allowed emission energies. That was quite a deep insight, and it was one of the things that really kicked off quantum mechanics at the beginning. The bottom line here, for our purposes, is that we're talking about waves, and we're talking about matter waves. So that uncertainty relation, or the relationship between the spreads of wavelengths and the spreads in positions that I mentioned in the context of Fourier analysis, will also potentially hold for matter. And that gets us into the position-momentum uncertainty relation. The wave-momentum relationship we just derived on the last slide was p equals h over lambda. This tells you that the momentum and the wavelength are related. From 2 slides ago, when we were talking about waves and whether or not you could say exactly where a wave was, we had a relationship that was something like delta lambda, the spread in wavelengths, times the spread in positions of the wave, is always greater than about equal to 1. Combining these relationships together in quantum mechanics, and this is not something that I'm doing rigorously now, I'm just waving my hands, gives you delta p, delta x is always greater than about equal to h bar over 2. And this is the correct mathematical expression of the Heisenberg Uncertainty Principle that we'll talk more about and derive more formally in Chapter 3. But for now, just realize that the position of a wave, the position of a particle, are uncertain quantities, and the uncertainties are related by this, which in one perspective results from consideration of adding many waves together in the context of Fourier analysis, which is something we'll talk about later as well, extended through the use of, or the interpretation of, matter as also a wave phenomenon. To check your understanding, Here are 4 possible wave packets, and I would like you to rank them in 2 different ways. 1, according to the uncertainties in their positions, and 2, according to the uncertainties in their momenta. So if you consider, say, wave B to have a very certain position, you would rank that one highest in terms of the certainty of its position. Perhaps you think wave B has a very low uncertainty in position, you would put it on the other end of the scale. I'm looking for something like the uncertainty of B is greater than the uncertainty of A is greater than the uncertainty of D is greater than the uncertainty of C for both position and momentum. The last comment I want to make in this lecture is on energy-time uncertainty. This was the other equation I gave you when I was talking about the boundary between classical physics and quantum physics. We had delta P delta X is greater than or equal to h bar over 2, and now we also had, excuse me for a moment here, delta E delta T greater than about equal to h bar over 2. Same sort of uncertainty relation, except now we're talking about spreads in energy and spreads in time. And I'd like to make an analogy between these 2 equations. Delta P and delta X. Delta P, according to de Broglie, is related to the wavelength, which is sort of a spatial frequency. It's the frequency of the wave in space. Delta X, of course, is just, well, I'll just say that's a space. And these are related, according to this equation. In the context of energy and time, we have the same sort of thing. Delta T, well, that's pretty clear, that's time. And delta E, well, that then, therefore, by analogy here, has to have something to do with the frequency of the wave now in time. And that's simple, that's just the frequency. The fact that these are also related by an uncertainty principle tells you that there's something about energy and frequency in time. And this is something that we'll talk about in more detail in the next lecture when we start digging into the Schrödinger equation. The time-dependent Schrödinger equation and deriving the time-independent Schrödinger equation, which will give us the relationship exactly. But for now, position and momentum, energy and time, are both talking about sort of wave phenomenon, except in the context of position and momentum, you're talking about wavelength, frequency of the wave in space, whereas energy and time, you're talking about the frequency of the wave in time, how quickly it oscillates. That's about all. The uncertainty principle, as I've said, is something that we'll treat in much more detail in Chapter 3. But for now, the uncertainty principle is important because you have these equations, and these are fundamental properties of the universe, if you want to think of them that way. And they're something that we're going to be working with as a way of checking the validity of quantum mechanics throughout the rest of throughout Chapter 2. That's all for now. You just need to conceptually understand how these wavelengths and positions or frequencies and times are interrelated. And the uncertainty principle is one way in which is the mathematical description. It's those relationships that I gave you earlier. Delta P, delta X is greater than about equal to h bar over 2. I think I just said greater than about equal to h bar earlier. We'll do things a little more mathematically here, and it turns out there's a factor of 2 there. That's some wave with a very specific wavelength. You can just think about it as a sinusoid. If I asked you to measure the wavelength of this wave, you could take a ruler and you could plop it down there and say, okay, well, how many inches are there? The key results from quantum mechanics, and it's related to what we discussed earlier in the context of the boundary between classical physics and quantum physics. Quantum mechanics has these inherent uncertainties that are built into the equations, built into the state, built into the nature of reality that we really can't surmount. To start off, though, conceptually think about position and wavelength. And this really is now in the context of a wave. So say I had a coordinate system here, something like this. And if I As an introduction to the uncertainty principle, we're going to talk about waves and how waves are related to each other. We'll get into a little bit of the context of Fourier analysis, which is something we'll come back to later. But the overall context of this lecture is the uncertainty principle. And the uncertainty principle is one of